Hello everyone, today we will be talking about 6VPE, IPv6 VPN Provider Edge, or 6VPE for short. It's a technology that uses IPv4 or MPLS to connect IPv6 islands. Why do we need 6VPE? As a next-generation network layer protocol, IPv6 not only provides a vast address space to allow more users and devices to access the internet, but also attract increasing attention due to its enhancements to service quality and security mechanism. However, evolving networks from IPv4 only to IPv6 only is a long and gradual process. In the meantime, the two types of networks will coexist. In the early stage of this process, IPv6 networks are not widely deployed, and IPv4 networks are still the most prevalent. At this time, IPv6 islands may occur. How can we connect these islands? In the previous video, we talked about 6PE. What exactly is the relationship between 6VPE and 6PE? Both have 6 and PE in their names, where 6 stands for IPv6. Where they differ is the V in 6VPE, which stands for VPN. 6PE is equivalent to placing all IPv6 networks connected through 6PE in one VPN. As a result, it can only be used for open and unprotected connection between IPv6 networks. 6VPE introduces VPN to provide logical isolation between connected IPv6 networks, improving IPv6 network security. How is 6VPE implemented? 6VPE implementation involves route advertisement and data forwarding. In this example, CE2 advertises a route to CE1, and CE1 forwards data to CE2. First, let's look at the 6VPE route advertisement process. Step 1. After a neighbor or peer relationship is established between CE2 and PE2, CE2 advertises a local IPv6 route to PE2. CE2 and PE2 use a standard IPv6 routing protocol for communication. Step 2. After receiving the route from CE2, PE2 adds an RD prefix to the route to convert it into a VPN IPv6 route. PE2 then advertises the route to PE1 through MP-BGP. After receiving the VPN IPv6 route, PE1 adds a route to its VPN IPv6 routing table and stores the MPLS label information carried in the MP-BGP update message. Step 3. PE1 exchanges routes with CE1 in a way similar to that in Step 1. They also uses a standard IPv6 routing protocol for communication. Next, let's take a look at the packet forwarding process of a 6VPE tunnel. 6VPE packet forwarding is similar to BGP or MPLS IP VPN packet forwarding. 6VPE adds double labels to an IPv6 packet so that the labeled IPv6 packet can pass through the IPv4 core network. The outer label is an MPLS tunnel label, indicating how to reach the BGP next hop. The inner label is a VPN IPv6 label, which is used to determine the outbound interface of the packet and the VPN to which the packet belongs. An IPv6 packet is transmitted through a 6VPE tunnel as follows. Step 1. CE2 sends an IPv6 packet to PE1. Step 2. Upon the receipt of the IPv6 packet, PE1 adds the inner label L2 and public tunnel label 1 to the packet. PE1 determines the inner label based on the IPv6 VRF and the public tunnel label based on IPv4 address information. Step 3. PE1 forwards the labeled IPv6 packet to P through a public network tunnel. P forwards the packet based on labels and is unaware of the inner IPv6 payload. Step 4. Upon the receipt, P swipes the outer label of the packet and then performs penultimate hoop popping or PHP to remove outer label L1. Step 5. After P receives the packet, it determines the corresponding VPN instance based on inner label L2 and then removes L2. Next, P2 forwards the original IPv6 packet to CA2 based on the destination address of the packet and the VRF table. IPv6 packets are forwarded between CEs and PEs, and MPLS packets are forwarded between PEs. MPLS tunnels are established based on IPv4 routes. Therefore, PEs must support IPv4 or IPv6 dual stack. Now let's have a look at 6VPE's features. The advantage of using 6VPE is that it can use the existing IPv4 or MPLS network to carry IPv6 services and requires only minor changes to IPv4 MPLS network to connect IPv6 networks. Connected IPv6 networks are unaware of the intermediate IPv4 network. That said, 6VPE also has some limitations. Specifically, it depends on MPLS and involves complex protocol status, especially RSVPTE status. PEs also need to support IPv4 or IPv6 dual stack, which consumes more CPU memory and other resources. As an interim solution for the initial stage of IPv4 to IPv6 transition, how will 6VPE evolve in the future? With the increased deployment of IPv6 networks, carrier networks now fully support IPv6. IPv6 networks can directly communicate through IPv6 without any transition technology. So, how can we provide IPv6 VPN services over the IPv6 backbone network? This is where SRv6 comes in. SRv6 uses existing IPv6 forwarding technologies and IPv6 extension headers to forward packets similarly to label-based forwarding, simplifying VPN implementation. SRv6 has obvious advantages for IPv6 networks. After SRv6 is deployed, the entire network runs IPv6, with PEs only needing to support the IPv6 stack. This helps conserve device resources. SRv6 packets have the same packet header as common IPv6 packets. Network nodes can communicate based purely on IPv6 reachability, simplifying network protocols and facilitating service provisioning. In addition, SRv6 provides flexible programmability to meet different SLA requirements of services. All in all, SRv6 performs better than 6VPE in IPv6 VPN implementation. Today, we have learned about the background and the implementation of 6VPE. You should now have a clear understanding of this technology.